Hi, I'm Tianyuan. This course project is about understanding cues and failure cases for nerve-based shape reconstruction algorithms. Recently, we see a lot of successful shape reconstruction algorithms using nerve-like rendering models. They produce very good-looking reconstruction results. And in this project, we try to understand what type of cues they are using for shape reconstruction, and try to analyze and experiment what kind of failure cases for this kind of algorithms. There are a lot of commonly used cues for shape reconstructions. Here, we briefly mention two of them. Shading is a complicated process that engages with the surface norm, the lighting direction, the viewer direction, and the object reflectance. It is widely used in shapeform shading and photometric theory. Shading tells surface norm information, so it is commonly used to recover fine-scale geometry. But to use shading cues, you need to jointly model the lighting, the geometry, and the reflectance of the objects, which makes the problem much more complicated and much less constrained. Multiview correspondence is another powerful cue. It has two big problems. First, it's hard to establish accurate correspondences for textureless region and for highly specular objects. Second, the error of triangulation grew quadratically with target distance, which makes it hard to produce fine-scale geometries. Nerve-based reconstruction algorithms integrate sentence and function fields with emissive volume renderers. The emissive volume renderer models consider each point in 3D as a particle that emits and absorbs light. This rendering model does not model shading. The removal of the shading makes the inverse problem much easier to optimize, but makes this type of algorithm hard to use shading codes. So through analysis, we can realize this algorithm majorly used multi-view correspondences cues. It can also use cues from object boundary and occlusions due to the remarching property. Through analysis, we hypothesize several potential failure cases for these algorithms. The first is transparent, specular, or textureless objects, which makes correspondences hard to establish. The second is inner reflections. Shading-based algorithm fails for concave objects with strong inner reflections. But multi-view correspondence-based methods may or may not fail. The third is fine-scale geometries, which we mentioned before that view correspondence-based algorithm is hard to recover. See the little bumps on the cup lid on the right. To verify these hypotheses, we select 5 objects around us following these descriptions. We put these objects on the checkerboard and capture around 15 images for each one of them. We use state-of-the-art structural motion to get a camera pose, and we run NURBS to reconstruct the shape. Since we don't have the ground truth geometry, we use visualization for the evaluation. The first is a transparent water bottom. Though it is transparent, we can see the overall shape looks good. I guess it is due to the cues from object boundary. We can see two strong artifacts. The first is small bumps on the flat checkerboard surface. The second is a blurry re-rendered image. The second example is a concave cup. We can see the recovery looks way more shallower than the real shape. I guess there are two reasons. The first, the texture for the inside of the cup is weak. Second, it's hard to use boundary cues for the recovery of the inside of the cup. The final example is about fine-scale geometry. See the text in the cup lid. We can see the reconstruction algorithm failed to produce this. Through analysis and experiments, my conclusion is that using emissive volume rendering models can only use cues from multi-view correspondences, boundary cues, and occlusion cues. It can definitely not using shading cues. So it fails for fine-scale geometries, and it also fails for textureless or specular part inside concave shapes. For more details, please refer to the report. Thanks.